Now that we've made these changes so that the term base class becomes the owner of all the pointers to all the objects, here's what our main function now looks like on slide 11. The top part is the same as what we looked at before. We're allocating two constants, one variable, then a plus, adding together the two constants, and a minus, adding together the first plus and the variable. We're then displaying the string and the value representation of that arithmetic expression. But instead of having to do 5 deletes of these individual terms, C1, C2, V1, P1, and M1, we can now invoke our base class static clear function, and that will take care of deleting all of the term objects so that we as the application developer are not responsible for counting them and making sure that we get them right. So this is good. We can use any term multiple times, and that's fine. The code is not too ugly now. It's not cluttered up with a whole bunch of deletes. One problem is that it assumes all term objects belong to the same arithmetic expression. So in our application, we would not be able to create multiple arithmetic expressions. And another problem, which seems minor but in fact is major, is that the application developer has to remember to call the term clear static function. Even very experienced developers regularly forget to close files that they've opened, regularly forget to delete objects that they've allocated with new, regularly forget to shut down access to a database that they have opened earlier in their application. Anytime you require an application developer to remember to close something or clear something or delete something or shut down something, that will inevitably lead to some bugs in programs. So we would like to eliminate this step as well. So here on slide 13, we're introducing a third way of dealing with the pointer ownership issue. Let's have each object be its own owner. So each object that is allocated is responsible for cleaning itself up. And this can be done using a standard so-called smart pointer type, specifically the shared pointer. The cool thing about shared pointers to objects is that when a shared pointer to an object goes out of scope, then the object that that shared pointer is pointing to is automatically going to be deleted. We don't have to worry about deleting objects ourselves. We don't have to worry about having a base class clear function that will do that for us. If we use shared pointers correctly, this will simply happen. Now, to use shared pointer, we have to include a standard header called memory. So here, starting on slide 14, is our code making use of shared pointers. We include memory. Our term base class is back to being the very simple thing that it was initially. It has a constructor that does nothing, a virtual destructor that does nothing, and two pure virtual functions, toString and toValue, so that term is an abstract class. The definition of the constant class and of its toString and toValue functions is not changed at all. In binary op, we do have to make a change so that we no longer have ordinary term pointers to keep track of the left and right children of the binary operator. Now we're using shared pointers to terms for the left and right values. Okay, so we simply replace term star with shared pointer and then term in angle brackets to indicate that we're using smart pointers to these left and right sides. The destructor for binary op now has nothing to do because the shared pointers will clean up after themselves. plus, shown here on slide 17, is a kind of binary op. We need to change the interface to the plus constructor to receive two shared pointers to term for the left and right operands of the plus. And these shared pointers are then simply passed down to the binary op base class constructor. A shared pointer can be used just like an ordinary pointer, so even though left is now a shared pointer to term rather than a term star, we can still say left arrow 2 string and likewise right arrow 2 string. We can use the same notation with the same expected functionality for shared pointers that we do with ordinary pointers. On slide 18 is our revised application using shared pointers. So instead of having C1 be an ordinary pointer to constant, we now say that C1 is a shared pointer to constant, initialized with the address of this newly allocated constant. Likewise, C2 is a shared pointer to constant, C3 is a shared pointer to constant, P1 is a shared pointer to plus, P2 is a shared pointer to plus, and these shared pointers all behave as ordinary pointers do, so that I can call P2 arrow string and P2 arrow 2 value. However, notice that at the bottom of main, I have no delete statements, I have no clear statement, because shared pointers, although they behave like pointers, they are in fact objects, and when they go out of scope, the destructors for these objects are automatically called, just as the destructor for any object that goes out of scope is called. And the destructor for the shared pointer will automatically do a delete of whatever dynamically allocated storage is being pointed to. So this is very nice because now we can have multiple uses of any term. We can use the constant C1 multiple times. We could declare a variable and use that multiple times, and so forth. And we don't have to delete anything. We just allow the shared pointer to clean up after itself. Now, it is true that using shared pointer is a messier syntax. Shared pointer angle bracket constant close angle bracket is surely more complicated to type than constant star. We could simplify things a little bit, maybe using typedef. But the advantages to using shared pointer, because we don't have to worry about deallocating anything, outweigh the little bit of syntax complication. So this business of keeping track of who owns the pointer and who is responsible for cleaning up or deleting or whatever the pointed to objects is not a trivial problem. And there are many approaches. None of them is perfect. The main thing is that you just have to think very carefully about this pointer management issue whenever you're dealing with dynamically allocated objects.